March 19, 2022. A MiG-31K interceptor climbed through Ukrainian airspace carrying beneath its fuselage a weapon Russian President Vladimir Putin had declared unstoppable. The Kh-47M2 Kinzhal hypersonic missile, capable of reaching Mach 10 and performing evasive maneuvers at altitudes where the atmosphere thins to near vacuum, represented Moscow's answer to American missile defense. Russian military doctrine claimed these weapons would penetrate any shield, arriving too fast and too unpredictably for detection systems designed to track ballistic trajectories. The missile released from its launch rail, its solid fuel motor igniting to accelerate the weapon toward a military depot near Ivano-Frankivsk in western Ukraine. Russian state media proclaimed the first combat use of an invincible technology. Yet 22,000 miles above Earth's surface, an array of American satellites had already detected the launch, tracked the missile's entire flight path, and transmitted precise trajectory data to ground stations across 3 continents. The supposedly invisible weapon had been visible from the moment it left the aircraft. Russian confidence in hypersonic weapons rested on fundamental assumptions about the limitations of American early warning systems. Soviet-era military planners had designed countermeasures around the capabilities of previous generations of infrared satellites, systems optimized to detect the massive thermal signatures of intercontinental ballistic missile launches from fixed silos or mobile launchers. Russian engineers believed that hypersonic weapons, with their lower initial boost phase signatures and ability to maneuver during flight, would exploit gaps in coverage optimized for traditional ballistic threats. The Kinzhal program, derived from the ground-launched Iskander-M short-range ballistic missile and modified for air launch, was specifically designed to complicate detection and tracking. By launching from high-altitude aircraft already deep inside contested airspace, the weapon would minimize its boost phase, the period when rocket motors produce the most distinctive infrared signature. Russian military theorists published assessments declaring that American space-based infrared systems, designed primarily for strategic warning of ICBM launches, lacked the sensitivity and coverage density to track tactical hypersonic weapons through their entire flight profile. Moscow's confidence extended beyond the Kinzhal to include the Avangard hypersonic glide vehicle, capable of riding atop an ICBM before separating and maneuvering through the upper atmosphere at speeds exceeding Mach 20, and the Tsirkin anti-ship hypersonic cruise missile, designed to destroy carrier battle groups before defensive systems could react. Each program represented billions of rubles invested in a capability Russian leadership believed would render American missile defense obsolete. The technology Russian commanders underestimated had been under development since the late 1990s, when American defense planners recognized that future threats would require persistent global infrared surveillance from space. The space-based infrared system, known by its acronym SBIRS, represented a generational leap beyond the Defense Support Program satellites that had provided strategic warning since the Cold War. Where DSB satellites used spinning sensor assemblies that scanned the Earth's surface in rotating sweeps, SBIRS employed staring focal plane arrays capable of continuous observation of vast areas with unprecedented sensitivity. The first SBIRS GEO satellite, positioned in geosynchronous orbit at an altitude of 22,300 miles, achieved operational capability in May 2013. From that vantage point, a single satellite could monitor an area spanning nearly one-third of the Earth's surface, its infrared sensors calibrated to detect temperature differentials as subtle as the exhaust plume from a theater ballistic missile in its boost phase. The system's scanning and staring modes worked in tandem, with wide-area scanning sensors detecting new events and cueing highly sensitive staring sensors to focus on specific regions for detailed tracking. By 2022, a constellation of 6 SBIRS satellites in geosynchronous and highly elliptical orbits provided complete global coverage, with multiple satellites able to observe the same geographic area simultaneously, eliminating blind spots and enabling precise triangulation of missile trajectories. The physics of hypersonic flight, rather than defeating infrared detection, actually enhanced the thermal signatures that space-based sensors were designed to exploit. When a vehicle travels through the atmosphere at speeds exceeding Mach 5, friction between the airframe and air molecules generates extreme temperatures. The nose cone and leading edges of a hypersonic weapon can reach temperatures between 3,000 and 5,000 degrees Fahrenheit, hot enough to melt most metals and ceramics. This heating is not merely a byproduct of velocity, but an unavoidable consequence of compressing atmospheric gases at supersonic speeds. The bow shock wave that forms ahead of the vehicle compresses air molecules so violently that their kinetic energy converts directly to heat, creating a plasma sheath around the weapon. Russian engineers had believed this plasma layer would absorb radar energy, making hypersonic weapons difficult to track with ground-based radars operating in traditional frequency bands. That assumption was correct. The plasma sheath does attenuate radio frequency signals in the gigahertz range, reducing radar cross-sections and complicating tracking by systems like Patriot or Aegis. But the same plasma sheath radiates intensely in the infrared spectrum. The ionized gases surrounding a hypersonic vehicle glow with thermal energy across multiple infrared wavelengths, creating a signature far more distinctive than the cooler exhaust plumes of subsonic cruise missiles. SBIRS sensors operating in both shortwave and midwave infrared bands detect this radiation with extraordinary clarity. The hotter the vehicle flies, the more visible it becomes to satellites specifically designed to track objects by their heat signatures. The technical specifications of SBIRS demonstrated why Russian confidence was misplaced. Each GEO satellite carried scanning sensors capable of surveying an area of 74 million square miles every 10 seconds, with sufficient sensitivity to detect the launch of tactical ballistic missiles with much smaller signatures than ICBMs. The staring sensors, once cued by a scanning detection, could track individual objects with angular resolution measured in microradians, precise enough to distinguish between multiple warheads separating from a single booster. The system's ability to operate in multiple infrared wavelengths allowed it to track targets through different phases of flight. Shortwave infrared sensors detected the intense heat of rocket motor plumes during boost phase, while midwave infrared sensors tracked the aerodynamic heating of vehicles in ballistic or hypersonic flight. This multispectral approach meant that even if a weapon's boost phase was brief or occurred below cloud cover, the vehicle would become visible as it accelerated through the upper atmosphere and began generating friction heating. The satellite constellation's architecture provided redundancy that eliminated single points of failure. At any given moment, at least 3 satellites could observe critical regions where hypersonic weapons might be launched, including Russian territory, Chinese coastal areas, and the Middle East. The overlapping coverage enabled stereoscopic tracking, using parallax measurements from multiple viewing angles to calculate precise three-dimensional trajectories. Data from the satellites transmitted to ground stations at Buckley Space Force Base in Colorado and Kena Point in Hawaii, where the Overhead Persistent Infrared Battlespace Awareness Center processed raw sensor data into actionable intelligence within seconds. If you appreciate discovering how classified technologies reshape the balance of military power, consider subscribing to Classified Warfare for future investigations into the sensors and systems that decide conflicts before the first shot is fired. The operational reality of hypersonic tracking became undeniable during the war in Ukraine. Between March 2022 and October 2025, Russia launched hundreds of Kinzhal missiles at Ukrainian targets, each strike intended to demonstrate the weapon's ability to overwhelm defenses. American satellites tracked every single launch. Intelligence assessments declassified in 2023 revealed that SBIRS had detected Kinzhal launches within 2 seconds of motor ignition, maintained continuous track through boost phase and mid-course flight, and provided accurate impact predictions that allowed Ukrainian air defense operators to vector Patriot interceptors toward the incoming threats. The first confirmed interception of a Kinzhal occurred on May 4, 2023, when a Patriot battery near Kyiv engaged and destroyed the missile during its terminal phase. The successful intercept was possible only because space-based sensors had provided early warning of the launch, tracked the weapon through its flight, and transmitted trajectory data that allowed ground-based radars to acquire the target despite the plasma sheath that would have made initial radar detection nearly impossible. Over the following months, Ukrainian forces using American-supplied Patriot systems shot down multiple Kinzhals, each interception representing a failure of Russian assumptions about hypersonic invulnerability. By October 2025, analysis showed that Russian hypersonic missile effectiveness had declined dramatically as Ukrainian operators learned to integrate space-based warning data with their terminal defense systems. The American response to the hypersonic threat extended beyond SBIRS to include next-generation systems designed specifically to track maneuvering weapons. The Next Generation Overhead Persistent Infrared System, abbreviated as NextGen OPIR, represented a comprehensive architecture combining satellites in geosynchronous medium Earth and low Earth orbits to provide layered tracking capability. The first next-gen OPIR GEO satellite, scheduled for launch in 2026, incorporated enhanced sensing capabilities and increased resilience to anti-satellite threats. Built on Lockheed Martin's LM-2100 combat bus, the satellite featured cyber-hardening, electronic warfare countermeasures, and autonomous threat response systems designed to continue operations even if ground control links were disrupted. The sensor payload included advanced focal plane arrays with significantly improved sensitivity compared to SBIRS, capable of detecting dimmer targets and tracking objects through denser cloud cover. Most critically, the system's tracking algorithms were optimized for hypersonic glide vehicles that maneuver during flight, using predictive modeling to anticipate course changes and maintain continuous custody even when targets execute evasive maneuvers. The architecture included a medium Earth orbit layer specifically designed to provide tracking handoff between the wide area coverage of GEO satellites and the detailed tracking provided by low Earth orbit constellations. The Hypersonic and Ballistic Tracking Space Sensor Program, known as HBTSS, filled a critical gap in the tracking architecture. Where SBIRS and next-gen OPIR GEO satellites provided strategic warning and initial detection, HBTSS satellites in low Earth orbit would provide continuous, high-resolution tracking of hypersonic threats from launch to impact. Orbiting at altitudes between 500 and 1,000 miles, significantly lower than the 22,000-mile altitude of GEO satellites, HBTSS sensors could observe targets from closer range with higher angular resolution. The lower orbit meant that individual satellites had smaller coverage footprints, requiring a constellation of dozens of satellites to provide global coverage, but the proximity enabled tracking updates measured in fractions of a second rather than seconds. Northrop Grumman, selected to develop the HBTSS prototype, completed critical design review in 2021 and delivered the first prototype satellite in 2023 for on-orbit testing. The test demonstrated the satellite's ability to acquire and track a maneuvering hypersonic glide vehicle within seconds of launch detection by GEO sensors, maintain continuous track through multiple course changes, and provide precision trajectory data sufficient for targeting by interceptor missiles. The test results validated the concept of layered infrared surveillance, with GEO satellites providing initial detection and cueing, medium Earth orbit satellites maintaining midcourse tracking, and low Earth orbit satellites providing terminal phase custody for fire control. The Space Development Agency's proliferated warfighter space architecture extended the tracking network into the hundreds of satellites. Rather than relying on a small number of expensive, highly capable satellites vulnerable to anti-satellite attack, the PWSA architecture distributed tracking capability across a large constellation of smaller, less expensive satellites in low Earth orbit. The tracking layer, developed by multiple contractors including Lockheed Martin and Northrop Grumman, consisted of satellites equipped with wide-field infrared sensors specifically optimized to detect and track hypersonic glide vehicles and maneuvering reentry vehicles. The first tranche of 8 tracking satellites launched in 2023, with subsequent tranches adding dozens more satellites annually. By 2028, the constellation was projected to include more than 300 satellites providing continuous, redundant coverage of the entire Earth. The proliferated architecture meant that even if adversaries destroyed multiple satellites, the network would continue functioning with minimal degradation. Each satellite communicated with its neighbors through optical crosslinks, creating a mesh network that could route tracking data between satellites and down to ground stations through multiple paths, eliminating single points of failure. The system's resilience against jamming and anti-satellite weapons represented a fundamental shift in space architecture, moving from vulnerable high-value assets to distributed, resilient networks that could continue operating in contested environments. Russian intelligence assessments obtained through signals intelligence and defector debriefings revealed growing awareness within the Russian military that hypersonic weapons had not achieved their promised invulnerability. A classified report from the main intelligence directorate of the Russian General Staff, dated November 2023 and subsequently leaked to Western intelligence agencies, acknowledged that American space-based systems were tracking Kinzhal launches with high probability and providing sufficient warning to enable defensive responses. The report noted that Ukrainian air defense forces were achieving interception rates against Kinzhals that should have been impossible if the weapons were truly undetectable. Russian electronic warfare units deployed to monitor Ukrainian Patriot radars reported that the systems were receiving external cueing data that allowed them to engage hypersonic targets despite the plasma sheath effects that should have prevented radar acquisition. The GRU assessment concluded that American satellites were detecting launches through infrared signatures and transmitting tracking data to Ukrainian forces through secure communications links, effectively negating the stealth advantages that hypersonic speed and maneuverability were supposed to provide. The report recommended urgent development of infrared signature reduction technologies, including active cooling systems for hypersonic vehicles and exhaust plume suppression techniques, but acknowledged that fundamental physics made it nearly impossible to eliminate the thermal signatures generated by sustained hypersonic flight through the atmosphere. Chinese hypersonic programs faced identical tracking challenges. The DF-17 medium-range ballistic missile, equipped with the DFZF hypersonic glide vehicle, represented China's primary hypersonic capability. First tested in 2014 and declared operational in 2019, the DFZF glided through the upper atmosphere at speeds exceeding Mach 5, capable of maneuvering to evade missile defenses. American intelligence assessments confirmed that SBIRS had tracked every DF-17 test launch, observing the initial ballistic trajectory as the missile climbed toward space, the separation of the glide vehicle from the booster, and the subsequent hypersonic glide phase as the vehicle descended toward its target. The tracking data revealed specific characteristics of Chinese hypersonic flight profiles, including typical glide altitudes between 40 and 100 kilometers, standard maneuver patterns, and thermal signatures that varied with vehicle speed and atmospheric density. This intelligence enabled development of defensive countermeasures specifically tailored to Chinese hypersonic weapons, including interceptor missiles optimized for exoatmospheric engagement before the glide vehicle entered its maneuvering phase. The People's Liberation Army Rocket Force, responsible for operating the DF-17, had reportedly expressed concerns similar to those of Russian commanders regarding the visibility of hypersonic launches to American space sensors. Chinese military publications from 2024 discussed the need for improved camouflage, concealment, and deception techniques to complicate satellite tracking, including mobile launcher operations from forested or mountainous terrain where infrared signatures might be partially obscured by terrain features and weather conditions. The physics of infrared detection from space provided fundamental advantages that no amount of Russian or Chinese engineering could overcome. The Stefan Boltzmann law of thermal radiation states that the power radiated by a blackbody is proportional to the fourth power of its absolute temperature. A hypersonic vehicle traveling at Mach 10, with a nose cone temperature of 4,000 degrees Fahrenheit, radiates infrared energy at wavelengths perfectly matched to the sensitivity peaks of space-based infrared sensors. The intensity of this radiation increases exponentially with temperature, meaning that small increases in velocity produce large increases in detectability. Russian efforts to reduce infrared signatures faced insurmountable constraints. Active cooling systems that might reduce surface temperatures would require carrying substantial amounts of cryogenic coolant, reducing payload capacity and adding weight that would limit range and maneuverability. Passive thermal protection systems using ablative materials or ceramic coatings could reduce peak temperatures slightly, but could not eliminate the fundamental heating caused by atmospheric compression. The plasma sheath itself radiated in the infrared spectrum as electrons and ions recombined, releasing energy as photons. Even if Russian engineers could somehow cool the vehicle's surface, the surrounding plasma would remain visible to satellites specifically designed to detect ionized gases. The only way to avoid detection would be to fly at speeds below Mach 5, eliminating the hypersonic advantage entirely, or to operate above the atmosphere where friction heating would not occur, which would require a ballistic trajectory vulnerable to conventional missile defense systems. American defensive systems evolved rapidly to exploit the tracking advantage provided by space-based sensors. The Aegis Ballistic Missile Defense System, deployed on Navy destroyers and cruisers, integrated SBIRS data feeds to provide early warning of hypersonic launches. The SPY-6 air and missile defense radar, with its advanced solid-state phased array capable of tracking hundreds of targets simultaneously, used satellite-derived trajectory predictions to focus radar energy on specific regions of sky where incoming hypersonic weapons were expected to appear. This queuing reduced the search volume from the entire hemisphere above the horizon to narrow corridors, allowing the radar to detect targets at maximum range despite plasma sheath attenuation. The SM-6 interceptor missile, with its active radar seeker and terminal guidance system, could engage hypersonic targets during their terminal phase when the weapons were decelerating and maneuvering to hit specific targets. The combination of space-based early warning, precision tracking, and advanced interceptors created a layered defense that Russian planners had assumed was impossible. Terminal high-altitude area defense batteries, positioned to protect critical facilities in Guam and Alaska, rehearsed engagement sequences against simulated hypersonic threats, using SBIRS data to practice interceptor launches timed to arrive at optimal engagement points. The successful intercepts of Kinzhal missiles by Patriot systems in Ukraine validated the kill chain that linked satellite detection, ground-based radar tracking, and interceptor guidance into a seamless defensive network. The intelligence value of tracking hypersonic tests extended beyond immediate defense to provide deep insights into adversary capabilities and intentions. Each Chinese DF-17 test generated gigabytes of sensor data analyzed by the National Air and Space Intelligence Center to characterize vehicle performance, maneuver authority, and operational doctrine. Analysts measured the glide vehicle's lift-to-drag ratio by observing how much altitude it lost during turns, revealing constraints on maneuverability that could be exploited by defensive systems. Thermal imaging showed hot spots on the vehicle's surface that indicated structural stress points and potential vulnerabilities. The timing and location of tests revealed which military units were training with the weapons and which targets were being simulated. Over multiple tests, patterns emerged that allowed intelligence analysts to predict operational employment strategies, including likely targets, preferred launch locations, and standard flight profiles. This intelligence fed directly into planning for defensive countermeasures and offensive operations. American strategic planners could identify which Chinese hypersonic units posed the greatest threat to forward-deployed forces, which critical nodes in the Chinese command and control network would need to be targeted to disrupt hypersonic operations, and which defensive assets should be positioned to provide optimal coverage against expected attack vectors. Russian attempts to counter American satellite tracking focused on electronic warfare and cyber operations rather than physical anti-satellite attacks that would create diplomatic crises and space debris hazards. Russian military doctrine emphasized non-kinetic methods to degrade enemy space capabilities, including jamming satellite communications, spoofing GPS signals, and conducting cyber attacks against ground control stations. The main Center for Reconnaissance of Situation in Space, Russia's Space Surveillance Command, operated ground-based lasers capable of dazzling optical sensors on low Earth orbit satellites, potentially blinding imaging satellites during critical observation windows. These capabilities posed genuine threats to some types of satellites, but were largely ineffective against SBIRS for fundamental technical reasons. The infrared sensors on SBIRS satellites operated in spectral bands different from those affected by ground-based laser dazzlers, which were optimized to blind visible light imaging systems. The satellites' geosynchronous orbits at altitudes exceeding 20,000 miles placed them beyond the effective range of most ground-based jamming and laser systems. The downlink communications used spread-spectrum encrypted transmissions with frequency hopping that resisted jamming attempts. Even if Russian electronic warfare systems managed to temporarily disrupt communications from one satellite, the redundant constellation architecture ensured that other satellites could observe the same geographic area and transmit data through alternate ground stations. The system's resilience against electronic attack reflected decades of design evolution, specifically intended to ensure that early warning of nuclear attack would remain available even during the opening phases of a conflict. China's approach to defeating satellite tracking emphasized proliferation of launch platforms and saturation attacks, rather than attempting to blind the sensors. People's Liberation Army planning documents discussed using large numbers of simultaneous launches to overwhelm American tracking capacity and complicate defensive responses. A saturation attack involving dozens of DF-17 missiles launched within minutes would generate hundreds of tracking targets as boosters separated from glide vehicles and decoys deployed to confuse sensors. Chinese military theorists argued that even if American satellites could track all objects, human operators and computer systems would struggle to prioritize threats and coordinate defensive responses against so many incoming weapons. This concept of attack assumed that tracking capacity was the primary constraint on American defenses. That assumption was incorrect. The SBIRS constellation, combined with next-gen OPIR and the proliferated tracking layer, could simultaneously track thousands of objects. The automated processing systems at the Overhead Persistent Infrared Battlespace Awareness Center used artificial intelligence algorithms to classify tracks, distinguish between threats and debris, prioritize targets based on trajectory predictions, and generate engagement recommendations without human intervention. Tests of the system during exercises involving simulated mass raids demonstrated the ability to maintain custody on more than 2,000 simultaneous tracks while providing fire control quality data on priority threats. The processing capacity was deliberately overbuilt to handle worst-case scenarios involving coordinated attacks by multiple adversaries launching hundreds of missiles simultaneously. Russian and Chinese development of fractional orbital bombardment systems represented another attempt to evade satellite tracking by launching weapons into low Earth orbit before deorbiting them over their targets. This approach, tested by the Soviet Union during the Cold War and revived by both Russia and China in the 2020s, theoretically allowed weapons to approach targets from unexpected directions, including over the South Pole where early warning radar coverage was limited. China conducted a test of a fractional orbital hypersonic weapon in July 2021 that Western intelligence agencies described as a significant development. The weapon launched on a Long March rocket, entered low Earth orbit, deployed a hypersonic glide vehicle that completed a partial orbit of the Earth before re-entering the atmosphere, and struck a target in the Gobi Desert. American officials publicly expressed concern about the test, calling it a demonstration of advanced capabilities that posed new challenges to missile defense. That public messaging, while accurate in describing the weapon's sophistication, obscured the fact that SBIRS had tracked the entire test from launch through orbital insertion, orbital flight, re-entry, and terminal phase. The satellite constellation observed the initial rocket launch from the Jiuquan Launch Complex, tracked the payload as it entered orbit, maintained custody during the orbital phase using space surveillance sensors, detected the deorbit burn, and observed the glide vehicle during its hypersonic re-entry and terminal approach. The test generated invaluable intelligence on Chinese intentions and capabilities, but it did not demonstrate any ability to evade American space-based tracking. The National Space Defense Center, responsible for coordinating military space operations, developed operational procedures to ensure that hypersonic tracking data reached combatant commanders with minimal latency. The center established direct communications links between the Overhead Persistent Infrared Battlespace Awareness Center and regional missile defense coordination centers in Colorado Springs, Pearl Harbor, and Stuttgart. When SBIRS detected a hypersonic launch, automated systems transmitted initial alert messages within 5 seconds of detection, providing launch location, azimuth, and preliminary trajectory estimates. As tracking data accumulated over the following seconds and minutes, the systems generated updated trajectory predictions with increasing accuracy, transmitted as a continuous stream of tracking messages to all relevant defensive units. The entire process from launch detection to transmission of fire control quality tracking data typically required less than 2 minutes, providing defensive systems with unprecedented warning time. For comparison, traditional ground-based radar systems would not detect an incoming hypersonic weapon until it appeared above the radar horizon, typically 1 to 3 minutes before impact depending on the weapon's trajectory and the radar's location. The additional warning time provided by satellite detection was sufficient to alert personnel, activate defensive systems, generate multiple engagement solutions, and launch interceptors with time for more than one shot if the first missed. Join us here at Classified Warfare as we continue investigating the sensors, satellites, and tracking systems that transform the balance of power between nations racing to deploy weapons they believed could not be stopped. The economic consequences of Russia's failed hypersonic strategy extended beyond wasted military investment to affect broader defense planning and resource allocation. Russia had invested heavily in hypersonic programs while neglecting conventional air defense systems, precision-guided munitions, and logistics infrastructure that proved critical during the war in Ukraine. The Kinzhal program alone reportedly consumed more than $5 billion from 2012 through 2022, with each missile costing an estimated $10 million. Russian military industry produced approximately 50 Kinzhals per year, a production rate constrained by the availability of specialized components and qualified technicians. These weapons, intended to provide Russia with a decisive advantage, instead proved vulnerable to Ukrainian air defenses receiving targeting data from American satellites. The strategic miscalculation forced Russian military planners to acknowledge that expensive, high-technology weapons provided little advantage if they could be tracked from launch to impact. Post-war analysis by Russian defense economists, leaked to Western intelligence agencies, estimated that the hypersonic programs had diverted resources from conventional capabilities that would have provided greater operational value. The same investment applied to producing larger numbers of conventional cruise missiles, improving electronic warfare systems, or modernizing tactical aviation would likely have generated better returns in terms of operational effectiveness. American defense planners drew different lessons from the demonstration of satellite tracking capabilities. The successful detection and tracking of every Russian and Chinese hypersonic test validated decades of investment in space-based infrared surveillance and demonstrated the continuing relevance of sensor networks that provided persistent global coverage. The Space Force, established as an independent service in 2019, received increased funding to accelerate deployment of next-gen OPIR HBTSS and the proliferated tracking layer. Congressional testimony from Space Force leadership emphasized that space-based tracking had become the foundation of integrated air and missile defense, providing warning time and tracking accuracy that ground-based sensors could not match. The successful tracking of hypersonic weapons also reinforced the importance of resilient space architectures that could survive attacks by adversary anti-satellite systems. Plans for the proliferated warfighter space architecture expanded to include additional satellite layers, including a custody layer optimized for continuous tracking of multiple simultaneous threats, a transport layer providing low-latency communications between satellites and ground stations, and a battle management layer processing tracking data and generating engagement commands. The total investment in these space-based capabilities exceeded $30 billion through 2030, a figure that defense officials justified by comparing the cost to the value of the early warning and tracking data provided. Hypersonic weapons remain dangerous threats despite their visibility to satellites. The combination of high speed and maneuverability created engagement challenges for defensive systems even when the weapons were tracked throughout their flight. An interceptor missile required precise knowledge of the target's position, velocity, and predicted future trajectory to calculate an optimal intercept point. Hypersonic weapons that maneuvered during flight complicated these calculations, forcing defensive systems to continuously update intercept solutions as the target changed course. The engagement geometry favored the attacker, who could approach from directions that minimized warning time and complicated defensive responses. A hypersonic glide vehicle approaching over the North Pole toward targets in the continental United States would be detected early by SBIRS, but might not enter the engagement envelope of ground-based interceptors until less than 5 minutes before impact, limiting the number of shots defensive systems could attempt. The combination of speed, maneuverability, and challenging engagement geometry meant that even with perfect tracking data, successful intercepts required advanced interceptor missiles, powerful radar systems, and sophisticated battle management networks. American missile defense architecture increasingly focused on layered defenses that could engage hypersonic threats at multiple points during their flight, using satellite-based tracking to enable exoatmospheric intercepts during the mid-course phase before the weapons entered their terminal maneuvers. The revelation that hypersonic weapons were fully visible to American satellites represented a strategic surprise in reverse. Russian and Chinese military planners had developed hypersonic capabilities, expecting that these weapons would be invisible to American early warning systems optimized for ballistic missile detection. They believed that the combination of speed, maneuverability, and plasma sheath effects would create a gap in American defenses that could be exploited to hold at risk critical targets including aircraft carriers, forward-deployed air bases, and command and control nodes. The discovery that every hypersonic launch was being tracked from space forced a fundamental reassessment of the value these weapons provided. If hypersonic missiles could be detected at launch and tracked continuously through their flight, they offered only marginal advantages over conventional ballistic missiles that were cheaper to produce and easier to maintain. The speed advantage of hypersonic weapons, which compressed defensive response timelines, was partially offset by the early warning advantage provided by satellite tracking. A hypersonic weapon that took 10 minutes to reach its target after launch provided 15 minutes of warning if satellites detected the launch 5 minutes before ground-based radars would have acquired the threat. This warning time advantage transformed the defensive equation, converting what Russian planners assumed would be a devastating first strike capability into a trackable threat that could be engaged by layered defenses. The political consequences of failed hypersonic invulnerability extended to Russian and Chinese strategic messaging and deterrence posturing. Both nations had used hypersonic weapons as symbols of technological prowess and military capability, showcasing them in military parades and state media productions that emphasized their unstoppable nature. Putin's March 2018 address to the Russian Federal Assembly featured animated videos of Kinzhal missiles evading American defenses and striking targets across Europe and North America. Chinese state media produced similar propaganda emphasizing the DF-17's ability to defeat American carrier strike groups. These narratives served domestic political purposes, demonstrating to Russian and Chinese audiences that their governments were investing in advanced military capabilities that would protect national interests. They also served strategic purposes, attempting to deter American military intervention in regional conflicts by threatening that interference would result in hypersonic strikes against American forces that could not be stopped. The demonstrated ability of American satellites to track hypersonic weapons and enable successful intercepts undermined these deterrent messages. American defense officials, initially cautious about publicly discussing satellite tracking capabilities, became more willing to acknowledge them after Ukrainian forces began successfully intercepting Kinzhals. Statements from the Department of Defense emphasized that the United States maintained comprehensive situational awareness of adversary missile launches and possessed the capability to track hypersonic threats throughout their flight profiles. Russian military journals published increasingly pessimistic assessments of hypersonic weapons' effectiveness as data accumulated from the war in Ukraine. Articles in Voyonnaya Missile, the theoretical journal of the Russian armed forces, acknowledged that American space-based surveillance had proven more capable than anticipated, and that hypersonic weapons had not achieved the level of invulnerability promised by their developers. Some authors questioned whether the continued development of even more advanced hypersonic systems, including scramjet-powered cruise missiles and air-breathing hypersonic platforms, represented wise investments of limited defense resources. These critiques remained carefully phrased to avoid direct criticism of political leadership or defense industry entities, but the underlying message was clear. Russian military professionals were recognizing that the hypersonic programs had been oversold and underdelivered. The weapons provided some operational advantages, particularly in their ability to complicate defensive engagement geometry, but they had not revolutionized warfare or rendered American defenses obsolete. The recognition that satellites had tracked every launch forced acknowledgement that Russia lacked a critical capability, comprehensive space-based surveillance of its own. While Russia operated limited early warning satellites for detecting ICBM launches, it did not possess anything comparable to the persistent global infrared surveillance provided by SBIRS. This asymmetry in space capabilities gave the United States a decisive advantage in situational awareness that Russia could not match without massive investment in satellite constellations it could not afford to build. Chinese military strategists conducted similar reassessments, published in classified studies produced by the Academy of Military Science and the PLA Strategic Support Force. These analyses, portions of which Western intelligence obtained through signals intelligence, acknowledged that hypersonic weapons alone could not defeat American integrated air and missile defense systems. Chinese planners concluded that effective employment of hypersonic weapons required comprehensive approaches including cyber attacks to disrupt satellite data transmission, electronic warfare to jam radar systems, kinetic anti-satellite strikes to degrade tracking networks, and saturation attacks using conventional missiles to exhaust defensive interceptor inventories before launching high-value hypersonic weapons. This more sophisticated operational concept recognized that individual technologies, no matter how advanced, could not overcome systemic advantages in sensors, battle management, and coordinated defenses. The Chinese emphasis on systems confrontation and systems destruction operations reflected lessons learned from observing Russian hypersonic employment in Ukraine, where individual weapon launches achieved limited operational value because American and NATO intelligence networks provided early warning and tracking that enabled effective defensive responses. The competitive cycle between hypersonic offensive capabilities and space-based tracking systems continued accelerating through the 2020s. Russian and Chinese engineers worked on reduced signature hypersonic vehicles, improved decoy systems, and operational concepts designed to complicate satellite tracking. American engineers responded with enhanced satellite sensors, improved tracking algorithms, and proliferated constellations that provided redundant coverage resilient to attacks. The fundamental asymmetry remained unchanged. Hypersonic weapons, by their physical nature, generated intense thermal signatures that space-based infrared sensors were specifically designed to detect. No amount of engineering could eliminate the heating caused by hypersonic flight through atmosphere. Russian and Chinese efforts to reduce infrared signatures could achieve marginal improvements, but could not make hypersonic weapons invisible. American efforts to improve tracking required incremental improvements in sensor sensitivity and processing capacity, achievable through evolutionary upgrades to existing systems. The cost-exchange ratio favored the defense. Building and operating satellites was expensive, but the cost of comprehensive global tracking capability distributed across hundreds of satellites was comparable to the cost of developing, producing, and maintaining sufficient numbers of hypersonic weapons to pose credible threats. The intelligence value of tracking adversary hypersonic tests provided strategic benefits that justified satellite costs independent of their defensive applications. The technological trajectory of missile tracking systems extended beyond infrared detection to include multiphenomenology sensors, combining infrared, visible light, radar, and electronic intelligence capabilities on single satellite platforms. Next-generation tracking satellites under development for deployment in the 2030s would carry sensor suites capable of detecting missile launches through multiple signatures simultaneously, cross-skewing between different sensor types to improve detection probability and tracking accuracy. These satellites would detect the radar emissions from missile defense radars illuminating hypersonic weapons, the visible light from rocket exhaust plumes, the infrared signatures from aerodynamic heating, and the radio frequency emissions from missile command links, fusing all these signatures into comprehensive tracks with redundancy against any single sensor being spoofed or degraded. The proliferation of commercial remote sensing satellites created additional opportunities for missile tracking. Private companies operating large constellations of imaging satellites for Earth observation possessed platforms that could potentially host missile warning sensors, multiplying the number of available sensors without requiring government investment in dedicated military satellites. Department of Defense studies examined options for hosted payloads on commercial satellites, compact infrared sensors that could be integrated into existing commercial platforms to provide additional tracking capacity at reduced cost. The strategic implications of comprehensive hypersonic tracking extended to nuclear deterrence and arms control. The ability to detect and track all missile launches, including those carrying nuclear weapons, reinforced strategic stability by ensuring that no nation could launch a disarming first strike without immediate detection. This transparency reduced the risk of miscalculation during crises by providing political and military leaders with accurate information about adversary actions. At the same time, the effectiveness of satellite tracking complicated arms control verification by making it more difficult for nations to conduct covert missile tests or hide the true capabilities of their strategic forces. Every test generated detailed intelligence that arms control negotiators could use to verify treaty compliance or document violations. Russian and Chinese resistance to certain arms control proposals reflected awareness that American intelligence capabilities would detect any violations, limiting their ability to gain advantages through clandestine treaty evasion. The transparency created by space-based tracking both stabilized deterrence and complicated diplomatic negotiations, a paradox that shaped strategic relations between nuclear powers. The final assessment of Russian hypersonic strategy reached an inescapable conclusion. Russia had invested billions of dollars developing weapons based on the assumption that American early warning systems could not track them. That assumption was wrong. American satellites had tracked every hypersonic launch, from the first Kinzhal test flights in 2016 through operational employment in Ukraine and beyond. The tracking capability existed because American defense planners, beginning in the late 1990s, recognized that future missile threats would require persistent global infrared surveillance from space, and invested in building systems with the sensitivity and coverage to detect all types of missile launches. Russian planners underestimated both the capability of existing systems and the pace of American improvements to space-based tracking networks. They assumed that satellites optimized for ICBM detection could not track tactical missiles with smaller signatures and more complex flight profiles. They were wrong. They assumed that plasma sheaths would make hypersonic vehicles invisible to tracking sensors. They were wrong. They assumed that the speed and maneuverability of hypersonic weapons would compensate for any detection and tracking that occurred. They were wrong. Every assumption underlying Russian confidence in hypersonic weapons proved incorrect when tested against the reality of American space-based surveillance. The demonstration occurred not through official statements or diplomatic channels, but through operational reality in the skies over Ukraine. Every Kinjal launch detected, every trajectory tracked, every impact location predicted. The supposedly unstoppable weapons were stopped, not by miracle defensive technologies, but by the systematic application of space-based sensors, ground-based interceptors, and battle management systems that turned tracking data into defensive actions. Russian military commanders, watching their expensive hypersonic weapons being shot down by systems they assumed could not engage them, confronted the consequences of their strategic miscalculation. The weapons they believed would change everything changed nothing fundamental about the balance between offense and defense. American satellites still saw everything. American intelligence still processed the data. American defensive systems still engaged the threats. The hypersonic revolution that Russian leaders promised delivered conventional weapons that flew very fast, cost enormous amounts to produce, and died like any other missile when tracked from space and engaged by competent defenses.